Okay, so let's get started. You're scribing today, right? Is that right? Okay, great. So yeah, at the end of last lecture, there were just maybe like a minute or 2 minutes more I wanted to say about main cost max flow, but ran out of time. So I just put that at the end of the notes, at the end of the lecture notes. You can go look at that. Today I want to, well, we only have 3 lectures left, I guess, including today. So I want to show you some more topics. Today I'm going to talk to you about another way of dealing with kind of NP-hard problems. So earlier in the course, we saw that one way was approximation algorithms, right? If you can't solve the problem in polytime, then maybe provably get a 2 approximation or log n approximation or something in polytime. Okay, so another way of dealing with it is actually solving the problem in exponential time. Okay, but then you want to make that exponential as small as possible. So, I'll put fast in quotes. Today it's today. We'll do fast in quotes exponential time algorithms. Okay, and we'll look at 3 ways of doing this. So exponential divide and conquer. So we're going to look at, for example, the traveling salesman problem. We're going to do pruned brute force. And also randomization. We'll see how to apply these things to like 3-sat. And we'll also see inclusion, exclusion. Also, kind of a similar thing. I think they're equivalent to each other. Is Mobius, fast Mobius transform. And inversion. And for this, we'll look at k-coloring. Okay, so these are a few different ways to speed up exponential time algorithms. Or in some cases, we're not going to actually speed things up. We're going to lower the space complexity. So there are some ways to get, say, exponential time 2 to the n time, but then the natural implementation would also have 2 to the n space. But we'll see that sometimes we can get the 2 to the n time while having only poly n space, things like that. Okay. So good. So let's just go through these techniques. Is there any question about anything? Well, I guess I didn't say much yet. So, okay. So the first thing, exponential divide and conquer. Okay, so the example I want to give you is TSP. Okay, so the input is a set P of points and a distance function D, which maps pairs of points to non-negative numbers. And let's assume it's a proper distance function. So this is a metric, so it satisfies triangle inequality and it's symmetric. Distances are 0 only if the 2 points are the same. And we're also given 2 identified points. ST, which are in P. Okay. And the goal is to visit every vertex exactly once. Okay, start at S, end at T, visit every other vertex exactly once, and the total length of your tour should be as small as possible. Have people here seen Traveling Salesman? Okay. find st path visiting each vertex once and minimize total length of path. So for the rest of the lecture, if I say O star of f of n, that means O of poly n times f of n. Okay, so I'm not really going to care too much about poly n factors. So what do we know about TSP? Okay, so what's the most straightforward algorithm? Let's look at both the time and space. And what do you, don't think, I mean, just,
try every path.
Yeah, try every path. So try basically all the orderings of the intermediate vertices. And there are n minus 2 factorial of them. And each one, you can sum up the length of the path. It takes about n time. So it's O star of n factorial. And the space is poly n. Okay, so this is brute force. Okay, 2. People I probably have seen something else. So something that to trade off the space for the time. So get time, which is much less than n factorial, but you're allowed to use, say, exponential space. Yeah. So dynamic programming. So yeah. So your time will be O star of 2 to the n, and your space will also be O star of 2 to the n. And this is dynamic programming. And the point is you can define a function, let's say, so you can say let f of x s be the length of the shortest xt path visiting every vertex, every point, I guess, every point in S once, where here S is a subset of the points, right? And what you want is f of s, comma, all the points. Well, you don't need s or t, right? So the number of states of your dynamic program are, well, how many current, so this is really like so you're currently at vertex S, you're trying to get to T, and you still need to visit everything in this set. That's what this means. Okay, so so this is an arbitrary subset that, like, throughout the execution of this algorithm, and you can write down an easy recurrence for this thing, right, where basically you try all possibilities for the next vertex to go to. Okay. So this, over the course of running the algorithm, could be any subset of this set. So there are 2 to the n minus 2 possibilities, roughly 2 to the n possibilities here, about n possibilities here. So the total number of states of this dynamic program is about n times 2 to the n. So your space is about n times 2 to the n. Okay. And your time, well, for each state, you need to loop over the next vertex to go to, which has about n possibilities. So your time will be like n squared times 2 to the n. So great. So we can get poly space with n factorial time, which is super exponential. It's like n to the n, which is like 2 to the n log n. Or exponential time with exponential space. And actually, it's an open problem to get O star 2 to the n time poly n space. It's not known how to do that. So what are we going to do instead? We're going to get something like O of 4 plus epsilon to the n time and poly n space. You know, for any epsilon bigger than 0.
Does epsilon appear in the exponent in polynomial n?
No. So there's no trade-off. So actually, I just did this to save myself writing. The actual time complexity is something like 4 to the n times roughly n to the log n. But that's at most 4.01 to the n, for example. Yeah, so I just shortcutted. Think of this as 4.01 to the n, or 4.001 to the n. Okay, and this is going to be via exponential divide and conquer. And it's actually a fairly simple recurrence, so let me write it down. So so let opt ust be length of the cheapest ST tour touching each point in U once. Okay. And what's divide and conquer? You try and split the problem in 2 or multiple roughly equal pieces or something, right? So what are we going to do? Well, the first half of the tour is going to go through some set, and the second half of the tour is going to go through some other set. We don't know what those sets are, so we try all possibilities. That's the whole algorithm. Okay, so opt of ust is the min over S being a subset of U. Let's say the size of S is the size of U over 2 plus 1. And let's also say ST union S is now U looks like U. So union T union S is everything, is U. And T intersect S is some point M. Okay? So we're trying all subsets of roughly half the size. And then we're also going to say, like, when we finish going through that half subset, where do we end up? And then that's where we pick up. That's where we pick up and continue in the second half. So we're going to go through half the points of U, call that S, and we're going to, when we finish going through S, we're going to end up at some point M. And then, now that we're at M, we have to finish going through T. So T is all the remaining points in U. Okay, and then now what's the, so what is it? So what's the best way to do this? Well, the best way is to go through S from S to M plus opt of, now we have to go from M to T. So yeah? Okay, great. And now we just compute opt of P, let's say PST, just recursively. Okay, just you don't have to do anything smart. Just do it by recursion. Okay. So the space complexity is pretty much just is definitely poly-n, right? Because at every point, you just really have to remember the current set that you're at, plus all the levels in the recursive stack above you, right? The depth of this recursion is no bigger than log of the number of points. And to remember the current set takes, again, at most n space. Okay, so this is poly-n space. How about the time? It satisfies a recurrence. T of n is the running time at n points. Is, oh, and then the recursive, like, when do you end this recursion? The base case is when just it's trivial, where basically s is only the point m or something like that. Or only the points s and m. So T of n, well, we have to pick m. So there are n minus 2 choices to pick m. And then we have to pick capital S as well. So that's something like times n minus 2, choose something like the seal of n minus 2 over 2. And then we get to decide for each partition into S and T, are we going to put little s on the capital S side or on the capital T side? Right. So there's some too. This doesn't really matter that much. And then times T of what's left. So whatever this, roughly n over 2. Okay. So if you solve this recurrence, so I'll leave it to you as an exercise. This recurrence solves to something like T of n, I think, is O of 4 to the n times n to some constant log n or something. Okay. So that's it. Okay. So that's a simple idea. I want to get into some of the other ideas we have here. Any questions about this, about the algorithm? Okay, great. So yeah, there's this kind of tantalizing open problem if you feel like it. Good. So how about next? So let's do. I want to show you this pruned brute force. So let's look at an example problem, which is 3-sat. So the input for 3-sat, what does that look like? It's a formula. What's the right? So let's call it phi, which is clause 1 and clause 2 and clause m. Each clause is an OR of 3 literals. So let's say xi1 or xi2 or xi3, and some of these can be negated. And let's say that there are n total variables. And the goal, decide whether there exists an assignment x equals a, which makes this phi evaluate to true. So people have seen 3-set. Yep. Okay. So good. So algorithms. Okay, so what's the most straightforward algorithm? Okay. So time is O star 2 to the n. Space is poly n. This is brute force. Okay, so let's look at how to do just a. We're still going to do brute force at first, but we're going to do a pruned version of brute force. Okay, so just notation. So given, so let's say, if I say like phi x or something like that, this is the new formula obtained from phi by setting, let's say x1 or something, by setting x1 to be true. And if I say like, phi x1 not x2, this is the new formula setting x1 to be 1 and x2 to be 0. Okay. So another way of going about brute force is keep doing the following. Pick, I'll just put it like this. Let C1 be some x or y or z. That's the first clause. So we know that, and one of them might be negated. We know that one of these things has to make the clause satisfied. So we'll just try all three. If the formula phi given x is satisfiable, return true. Okay, but maybe it's not. So then we'll try setting y to be 0. Else, if it's possible to satisfy phi y bar, return true. Else, if satisfiable phi z, return true. Else, return false. So this algorithm here is my set algorithm. Okay, so it's a recursive algorithm. And there's some base case I didn't bother writing, right? So once the formula is empty, you just say true. So what's the running time? What's the recurrence for the running time? N is the number of variables. Yeah, 3. This is at most, 3 times t, and then minus 1, plus some poly-n or something. Which is, when you solve it, O star of 3 to the n. Which is worse than that other one where you just try everything. But so now we're going to get into pruned brute force. So what's one thing you can do to optimize this code? Yeah.
When you try to set x to 1,
Yeah.
if any other clause has x in it,
Yeah.
then this one is satisfied, so you can just remove it.
Sure. So you're saying when I set x to 1, before this recursive call, I can go through the formula and simplify everything that is already now satisfied because x is 1. Yeah, you can do that. And also, all the clauses which have not x in them, you can remove the not x and make it have only 2 literals in it instead of 3. You can do that. Yeah, what's something else you can do?
The else thing, you can actually assume that x is set to false.
Yeah, you can assume it, right? You can assume x is set to false because here, if we ever get to this else, it's because this returned false, which means that there is no satisfying assignment where x is true. So from now on, we can just assume that x is actually false. Right? Yeah?
Sorry, should that be m, like the number of clauses instead of?
Oh, here? Yeah, but m is at most n cubed or something. Yeah. Yeah, that's, yeah. Let me see. So note m is O of n cubed, right? The number of possible clauses on n variables where each clause has only 3 variables in it, or 3 literals, is at most 8 times n choose 3 or something. 8 because you can choose if it's in negated or not. Something. Okay, and again, when you get to here, you know that it's not possible to have y being set to 0 and still satisfy this thing. So you can also, right, you can also assume that you have y set to true now. So this yellow version is now the pruned brute force that I mentioned. And when you do the pruned one, you get t of n is at most t of n minus 1 plus t of n minus 2 plus t of n minus 3 plus poly n. And when you solve this recurrence, you can show that this thing is something like 1.8 something or other to the n. Okay, so it's the so this call this constant c. C is the largest root of the equation x cubed minus x squared minus x minus 1 is equal to 0. Okay, so you can kind of play these games in more and more complicated ways. Okay, so you can say if I'm doing this recursive call, I can assume that there exists a clause which has only two literals, and then et cetera, and just kind of reason through the actual recursion tree and prune things away. Okay, and you can make this constant smaller and smaller by doing that. Okay, and there are a lot of papers that did that for a while. Let me show you other things you can do, and then I'll show you one algorithm that is a totally different approach, which was the record for a brief moment, about a little more than 10 years ago. And I think even the current algorithm, which holds the record, is more along the lines of that approach than this kind of pruned recursion tree approach. Okay. Okay, so let me show you another smarter brute force. Okay, so without loss of generality, we know. So okay, let's say suppose A star satisfies phi. So phi is satisfiable. If it's not satisfiable, then the algorithm I'm going to tell you is just going to not find a satisfying assignment, and we're going to output that it's not satisfiable. Okay, so without loss of generality, we know an assignment A such that the distance, the Hamming distance, the number of variables where the assignments differ, is at most n over 2. Why do we know that? Why do we know such an assignment?
For any assignment, either this or the negation.
When you say this or the negation of what? So we don't know A star. I'm saying in our algorithm, we're going to assume our algorithm knows something that's within n over 2 of A star.
So you can pick any assignment A,
Yeah.
run the algorithm, and then pick
Oh, I see.
negation A and run the algorithm.
Right. Right. So yeah. As Jarek said, just take our A to be the all 0 string, and if that's not within n over 2, then the all 1 string will be within n over 2. Okay. So take any assignment and its negation. So we might have to run what I say twice, one for the all 0s and one for the all 1s. Okay. And now what do we do? So we're going to try and fix. So we know that we're only off on n over 2 variables, but we don't know which ones they are. But we're going to try and fix those n over 2 variables. Okay, so while there exists an unsatisfied clause C, pick one of the variables in C and flip its assignment okay. one will stop this loop after n over 2 iterations. So if this loop goes on for more than n over 2 iterations, we just quit. OK, so here's the point. If our assignment is not a satisfying assignment, and that means there's some clause which is not satisfied, so we must be wrong. Our assignment must differ from A star on at least one of the variables in that assignment. Right? So we don't know which one of the three it differs on. So what do we do? Yeah, OK, so yeah, we're going to get there. Pick one randomly, but just try all three. Try all three in a brute force way. OK? Just recursively. And if none of those worked, OK, then we're out of luck. Right, so as we're doing this brute force in this trying all three, if there actually was such a satisfying assignment A star, then there will be a recursion path of depth n over 2, where we actually made the right guess every time as to which thing we differed on. And then we would actually halt with A star, or some satisfying assignment. Right? So what's the running time of this algorithm? Are people clear on what the algorithm is?
You say there's some recursion path of length n over 2, but here we just stop after the first recursion path we happen to choose, right?
Oh, so I should really say try each of the variables in C recursively and flip its. So for each of the variables in C, flip its assignment in A, and then continue recursively back to the. I guess I didn't say this. Is it maybe it's unclear what the algorithm is?
So we stop after n over 2 recursion depths.
Yeah. So we imagine a brute force recursion, which does the following. Okay, the brute force recursion does the following. It finds an unsatisfied clause, and then it looks at the three variables in that clause, and it recursively tries to flip each one of those three. So it flips the first one and recursively runs the same thing. And then it flips the second one, recursively runs the same thing, et cetera. And if the recursion depth ever goes more than n over 2, it just like quits this. It doesn't go any further into the recursion. Right? So the point is, if we're actually at distance at most n over 2 from A star, there will be some path in this recursion tree that made the right guess on every stage, and then we would actually find A star. The only time this would fail is if there were no satisfying assignment, or if we were more than n over 2 away, in which case the negation of the initial satisfying assignment would have worked. Okay. So what's the running time of this algorithm? Sorry? Yeah, root 3 to the n, right? So the runtime is O star of 3 to the n over 2, which is root 3 to the n. And root 3 is something like, what is root 3? 1.7321. Okay, so that's another algorithm that gets a better base in the exponent. So now I want to tell you an algorithm which looks similar to this algorithm, but yeah, it's going to do something random, as you said, and it's going to get a really good bound, which is the base of kind of the best known ones now. So randomization. So I'm going to show you Cherning's algorithm. And the journal version was in 2002. It's going to get time, which is O star of 4/3 to the n, and space poly n. The current record I hope I got this right. It was annoying tracking this down because every time I thought I found the new fastest algorithm, I realized that 4 months later or something, someone shaved a 0.01. So let's see, what did I find? Oh, did I write it? I thought I wrote it. Yeah, here we go. So if you're randomized, so you can get time, which is something like O to the 1.30704. This is Hartley COMP 2014. And then deterministic algorithms. You can get 1.3303 to the n. This is Tamaki. So I think some of these algorithms, anyway, they, I mean, this is true not just of these algorithms, but of algorithms that that were shown before. They kind of take different ideas, like they combine this pruning approach with the randomization approach, and they show that kind of the min of the two has to do well or something of that flavor. Okay, so I mean, there's more that goes on as well, but every time there's a new idea, you can like combine it. You often can combine it with the previous ideas to make the resulting algorithm even faster than either of them. Okay, so let me write down the algorithm. So let's say algorithm, before I tell you what Scherning's algorithm is, it uses the following subroutine, and then once we have the subroutine, the algorithm is basically run the subroutine lots of times. Okay, so let's call it algorithm S. So 1, pick A uniformly at random. And 2, repeat at most t times. Let C be the first clause not satisfied by A. Flip a random variable in C. Oh. And that's it. So that's the algorithm. Okay.
What is T?
Yeah, so T is going to be a parameter that we're going to set. So yeah, we'll set T. Okay, questions about the algorithm? I mean, actually, we're going to run T. We're going to end up running it in the actual algorithm with T being like n. Have people seen the randomized? I think, well, anyone who took a CS 124, I guess, last semester would have seen it. But I'm curious, how many people have seen this random walk kind of algorithm for 2-sat instead of 3-sat? So, okay, so some subset. So you can do the same thing for, KSAT, right? You can pick a random assignment, and then as long as there exists an unsatisfied clause, flip a random variable in that clause, and keep going until it's satisfied or until too much time has elapsed, and then you give up. Okay. Actually, no, what did I say? Did I say we're going to run it with t being n? No, we're going to run it with t being 4/3 to the n. Or you can think about it also as we're going to run it with t being n, and then we're going to do this algorithm multiple times. So with 2-sat, so there's a similar algorithm for 2-sat as due to Papadumitriou and I think Fox 91, something like that. Okay. So you can show that for 2-sat, if you run this for about n² steps, 100 n² steps or something, if there actually is a satisfying assignment, you'll find it with probability at least 2/3. So you can drive that error down by just running this algorithm, log 1 over delta times. And if none of those iterations ever find something, you'll just output fail. Okay, so that's an algorithm that if there actually is a satisfying assignment, you might not find it with probability delta. But with high probability, you'll find it. And how do you analyze such an algorithm as the one above? So we're going to do it via Markov chains. Who here has seen Markov chains or knows what a Markov chain is? Okay, so most of you, but let's just recap. So Markov chain is a directed graph. Okay, and every edge E has a probability associated with it, PE. And for all vertices V, the sum over E leaving V of PE should be 1. So it basically tells you, you imagine that you're moving around vertices in this graph. At every step, there's a distribution over which neighbor you're going to go to next. Okay, that's told to you by these edge probabilities. In our case, the graph G is a path on n vertices, or n plus 1. Okay, and vertex I represents that the distance from A to A star is equal to I. So here's our graph. It doesn't represent a specific assignment. So there are many assignments which might map to the same vertex. It only looks at the distance between our current assignment A and some fixed. There might be multiple satisfying assignments A star, We're just going to fix one of them, and we're going to look at the distance to that. So initially, we picked a at random. So initially, the distance is some random number between 0 and n over 2, and n. It'll most likely be somewhere around n over 2. Right? So initially, we're here. And then at every step, we pick a clause that's unsatisfied, and we flip one of the variables in it at random. Okay? So either that variable we already agreed with a star, in which case, by flipping it, we're making ourselves agree less, which means we go to the right, we increase the distance. Or we actually did disagree on that variable that we flipped, in which case now we agree, so the distance went down. So actually all of these are there. It's a directed graph, so there's like it's sort of like this, right? So at every step we can go left or right, and then at n, well, actually at n there's no right, and at 0 there's no left. So from 0, this probability is 1. We're definitely going to, if we're already there and we flip something, we're going to just increase the distance. And if we're at n, if we flip something, we're going to decrease the distance. How about any of the intermediate people? So we know that, let's say that we're currently here. We're at distance 2. So this is distance 1, this is distance 2. So we pick a clause that's not satisfied. How many, we know then how many, we can say that we disagree with a star on at least one variable in that clause, right? So there are 3 variables. We disagree with at least one. So our probability of going left is at least a third. And our probability of going right, or going right here, is at most 2/3. Does that make sense? This is true for all the intermediate vertices. Now, our algorithm might halt with a satisfying assignment without actually getting to 0, because it might happen to find another satisfying assignment. But that's only better for us, right? So what we're going to analyze is we're going to say, look, if you're at some vertex, what's the expected time before you get to 0? But if you halt and find the assignment even faster than that, then that's, we're only upper bounding your time anyway. So let's simplify our lives. By instead just looking at kind of the infinite path. So here's n minus 1, and here's 0. But there's also minus 1 over here. There's also minus 2, et cetera. There's also n plus 1, et cetera. And every single one of these, you go right with probability exactly 2/3, and you go left with probability exactly 1/3. Let's look at this Markov chain instead. Right? I claim that if you can prove an upper bound on the time to get to 0 in this Markov chain, starting from somewhere between 0 and n, then that's going to be an upper bound on the time to get to 0 in that Markov chain. Right? You can only get there faster. So let's look at this thing. And in fact, what I'm going to do is I'm going to look at the probability that we get. I'm going to make it even harder for us. And I'm going to say, not only am I going to, so here we're OK as long as we get there within t steps. I'm going to say, what's the probability that we get there exactly on the tth step? Okay, so if we got there at time t minus 1 or t over 2, I'm not even going to count it. We have to get there in exactly t steps. Okay, and even with this pessimistic view on the world, we're still going to get our 4/3 to the n bound. So let's say we start off at distance k. What's the probability that we get to 0 after exactly t equals, we land at 0. At exactly, let's say, at exactly time t being 3k. So really what we're going to do is we're going to run this because we don't really know what k is, right? But as long as we're running it at least 3k steps, this analysis will apply. And so we can set t to be like 3n. Then definitely the 3k mark will have passed. And then we're gonna show that this thing is going to be at least something like 3/4 to the n, roughly. Okay. So then what do you do now to get an algorithm which runs in time 4/3 to the n? Well, we know that every trial you succeed with probability roughly 3/4 to the n. So repeat it. You succeed with probability p. So repeat it 1 over p times, and you expect to succeed at least once. And that's where the 4/3 to the n is going to come from. Does that make sense? So okay. Good. So what do I want to say? In fact, more specifically, probably that make k steps to the right and 2k steps to the left is at least what? So I'm going to look at this specific way of succeeding. Okay, so the problem that we make exactly k steps to the right and 2k steps to the left in our walk of length 3k is, well, 3k choose k times 1 over 3 to the k, 2k, times 2/3 to the k. Okay. And now let's just do a little Stirling's formula. 3k choose k is equal to 3k factorial over k factorial 2k factorial, which, if you remember, Stirling says that n factorial is theta root n over e to the n, right? So this is, well, if you just do this thing to that, you get something like, this is theta of 1 over root k, 3 to the 3k over 2 to the 2k. So just take my word for it, that's what you get. So let's call this star. That implies that star is theta of 1 over root k, 1/3 to the 2k, 2/3 to the k, times 3 to the 3k over 2 to the 2k, which, if I didn't mess up in my preparation, should be 1 1 over root k times 1 over 2 to the k. Hey, does that look right? So here you have a 3 to the 2k. Whoa. Am I? Good. Here you have a 3 to the 2k. Here you have a 3 to the k. That completely kills this 3 to the 3k. And then here you have 2 to the k and 2 to the 2k. That makes it 1 over 2 to the k. Okay, great. So this is 1 over root k, 1 over 2 to the k. Okay, great. Okay, but that's as a function of k, but we don't know k. So what do? We sum up over all possibilities for k. The probability that we find satisfying assignment is at least the sum over k. K can go from 0 to n. Probability that distance a and a star is equal to k times some theta of 1 over root k times 1 over 2 to the k. Okay. So what's the probability that the distance between a and a star is exactly equal to k? Well, I guess it should be something like n choose k times 1 over 2 to the n or something like that. So this thing is at least up to a constant. Let's pull this 1 over root k is definitely at least 1 over root n. So 1 over root n, 2 to the n. No, let me not. Let me just put 1 over root n times a sum over k. Well, okay, so I shouldn't divide by 0. I mean, if k is 0, then we're done in the first step anyway. Okay. 1 over 2 to the n plus k. So n choose k. 1 over 2 to the n plus k. Okay, so this thing I claim is basically equal to 3/4 to the n minus some constant. Why is that the case? Does anyone see this? There's just a slight trick here. Yeah, so basically, just look at 1/2 plus 1/4 to the n and expand it, right? And what do you get? You get, is that right? Yeah, so you can choose to get the 1/2 n minus k times, and then you'll get the 4k times. So 1/2 to the n minus k times 1/4 to the k is exactly 1 over 2 to the n plus k. And there are n choose k ways of doing that. So really, this is the expansion of this, except we're missing the k equals 0 term. The k equals 0 term gives you n choose 0, 1 over 2 to the n or something. So you're losing the 1 over 2 to the n. So this is exactly equal to this minus 1 over 2 to the n. So this whole thing is at least 1 over root n times 3/4 to the n. Okay. So this thing here I'm going to call, P. So our success probability is p. So if we run this thing, p times log 1 over p times log 1 over delta times, the probability that we never find a satisfying assignment is at most delta. So this is our 4/3 to the n, O star 4/3 to the n algorithm. Questions about that? Yeah, so I mean, I mentioned some of these bounds which came after Scherning's algorithm that drive down the 4/3 to 1.30 whatever. Yeah.
So you mentioned the same idea for two-set quadratic time algorithm.
Sorry, say it again.
So you said the same randomized idea for
Yeah, yeah,
quadratic time.
yeah.
But don't we already know linear time?
Oh yeah, we do.
So what's the point of this Fox paper?
Oh, actually, I think his paper was not. I didn't read that paper, but I did look at the abstract. So you're saying we already know an n plus m time algorithm for 2-sat, so who cares about n squared? So I looked at I didn't read this Fox 91 paper, but I looked at the abstract, and he sort of just mentions it as like an aside in the last sentence, like, oh, and by the way, it follows that we get this 2-sat algorithm. His paper was actually about something else. I don't remember what his paper was actually about, but he just observed that, by the way, this gives a simple 2-sat algorithm. Okay, good. So in the last 15 minutes and change, I want to tell you a little bit about inclusion, exclusion, and k-coloring. And we'll see also this fast Mobius transform and inversion. Okay. Any questions about this before I move on?
Oh, wait, so
Yeah.
these other papers remove like all of the making it harder for ourselves to do, like, moving the endpoints and assuming that we do exactly this number of steps in each direction.
Oh, you mean the ones that beat the 4/3 to the n? So this paper of Scherning that gets this kind of thing. So, okay, good. So let me say a little bit more. There is something more, slightly fancier you can do, which I think improves the Pauli factor. Like, I think you might not actually need this 1 over root n. Maybe I'm wrong about that. But the paper, so Scherning's algorithm really gets 4/3 to the n, up to this O star. Then the papers afterward, which got improvements, it was not only by twiddling around with better analysis of this. There were other ideas as well. But I don't know those papers very well, so I shouldn't. Okay. So let me do inclusion, exclusion. So what is inclusion, exclusion? Well, here's one way of writing it. So next topic. So no more questions about 3-sat?
Just
Yeah.
a final question.
Yeah.
So with these algorithms, what's the largest kind of three-set problem we can hope to solve on our computer today?
Oh, so I think in real life, people use other kind of heuristic, not heuristic, but so people use this thing called, was it DPLL, which I think is really fast in practice for SAT instances you'll actually see. So SAT is one of these funny problems where there are systems out there that routinely solve large SAT instances, even though it's supposedly NP hard. And the reason is that the NP hard instances are not, they're sort of rare, and you have to like craft them. I mean, no, I shouldn't say, what am I saying, NP hard instances. A problem is NP hard, not an instance. Okay, so a lot of the instances that people come across in real life turn out to be easy to solve via some algorithms like DPLL. You have to like work hard to come up with instances that will break those algorithms. So yeah, so people aren't actually running the 4/3 to the n algorithm. Okay, good. So so the next thing I want to tell you about, the next technique will be inclusion exclusion. Okay, so what is inclusion exclusion? So theorem. So for any sets R subset equal to T, we have the identity that the sum over S sandwiched in between them of -1 to the size of T the set difference okay, is equal to R equals T. So okay, so have people seen this before, this statement? This? So whenever I have like a logical statement, P, bracket P evaluates to 1 if P is true and 0 if P is false. So this summation is either going to be 1 if R is equal to T, meaning that there's only one set that's in the middle, namely T itself. And if R is not equal to T, then this summation is 0. Okay? And why is that? Well, if R is equal to T, as I said, the only thing in the middle is S equals T, in which case this difference has size 0, and -1 to the 0 is 1. Okay. If R is not equal to T, then we're going to set up a bijection between the odd-sized sets T / T minus S and the even-sized sets T minus S. What's that bijection? I should also say for any non-empty, for any sets, or T is not empty. Okay. Oh, I don't really need to say that actually, because if T is empty, then R is empty too. Okay, so I always get worried about empty sets and zeros. These base cases, these are sources of bugs. Anyway, if R is not equal to T, so let's just write down a very simple proof. Proof R equals T implies the summation of R subset S subset T is just the sum over S equals T of -1 to the 0, which is 1. If R is not equal to T, pick some T in the difference. And then we set up a bijection between T minus S even between S such that T minus S even and S such that this thing is odd. So what's the bijection? A maps to A symmetric like kind of, what do you call this, XOR? I don't know if this is, what do you say for sets? Well, I'll say what I mean. Take a set A. What's the bijection? If it has T in it, remove it. If it doesn't have T in it, put it in. This is a bijection between the odd and even size sets. So we know that there's exactly an equal number of sets where this thing is even versus odd, so this whole thing is 0. Okay. So now we want to use inclusion-exclusion to design good algorithms. So let's look at an example problem. K-coloring. Okay. So the input is a graph, undirected graph. G equals VE. And let's say the size of V is n, the size of E is m. K coloring is a function C of C, which maps V into 1 up to K, such that if there's an edge UV in the edge set, it implies that C of U is not equal to C of V. Okay? So we have to color vertices in such a way that adjacent vertices do not have the same color. And the goal is to decide if K coloring exists. Okay. Good. Notice that it's equivalent, an equivalent question decide, or equivalent problem, decide if a V can be partitioned into K independent sets. What's an independent set? An independent set is a set of vertices such that there are no edges between any vertices in that set. So if you can partition, so these questions are equivalent. Why? If you can partition into K independent sets, then everything that goes in the first set, you'll give color 1, the next set color 2, okay? And then you know that it's a valid K coloring. Now, how about the other direction? If you had a valid K coloring, then what would your partition be? Everyone that had color 1 would be 1 partition. Everyone that had color 2 would be partition 2, et cetera. So these are equivalent problems. Okay? So we're going to focus on this version. Now, what are some algorithms for K colorability? Someone tell me some. Brute force. Okay, I'll just tell you brute force. So brute force, O star of K to the n is just time, poly n space. This is brute force. Okay, how about something smarter? Does anyone know what you can do that's better than, say you don't care about space, you want to get better time. What do people know? Dynamic programming. Yeah, we've seen that so much today. So what kind of, does anyone know what time you would get out of dynamic programming? I'll tell you what the dynamic program is. So kind of you're trying to compute f of r s is 1, if possible, to partition S into R independent sets, and 0 otherwise. And we want f of kv, right? And there's a simple recursion to compute f of rs. Basically, just loop over all subsets, capital R. Let me not use R twice. Okay, so there's a simple recursion to compute capital F of TS. Loop over all subsets R of S. And if R is an independent set, then now try and see if F of T minus 1, S minus R is possible. Right? So the space of this, you have to remember T. That's just at most k. This is a number that's at most k. You have to remember this subset S. There's 2 to the n possibilities. And within each for each state of the dp, you have this recursion that's trying all subsets of that. So definitely the time is at most 4 to the n, right? For every subset, you loop over all subsets. Actually, the time is even 3 to the n. Do people see why the time is 3 to the n? Right, so the time is O star is, let's say, at most star, that's O star for my made-up notation, of the sum over all s's subset of v of roughly 2 to the s, right? Which is the same thing as the sum, well, what's the size of s? The size of s is anything from 1 up to n of n choose I, because I can choose the set S, there are n choose I possibilities, times 2 to the I. Here's one way of interpreting this summation. I have a string where every digit in the string is either 0, 1, or 2. I choose I of the digits to not be 0. Okay, so I loop over all I. I choose I of the digits to not be 0. All the other ones are 0. And then from the ones that are not 0, I choose if it's going to be 1 or 2. So there are 2 to the I possibilities for that. So this counts the total number of strings of length n where all the digits are 0, 1, or 2. So this is exactly 3 to the n minus 1, because I didn't count the all 0 string. So the time is O star 3 to the n, and the space is poly n. No, the space is what am I saying is O star 2 to the n. Because I have to remember all these sets, right? S can be one of 2 to the n possibilities. Inclusion exclusion, on the other hand, oh, whoa, let me not erase. 0. Great. Okay. I think I'll actually be able to finish saying this. Inclusion exclusion, you can either get O star of 3 to the n time and poly n space, or O star 2 to the n time and space. Okay, and how does that work? Let's define f of s to be 1 if S is a non-empty independent set, and 0 otherwise, and define the, well, it's called the zeta transform. I think it's Fourier transform, except it's not. F hat of S to be the sum over all r's subset are equal to S of f of S. Okay. It just counts how many subsets of S are non-empty independent sets. And the claim is that G is K colorable if and only if the sum over all S's subset of the vertices, -1 to the n minus the size of S, G of S to the K is bigger than 0. Okay?
In f hat, is it sum?
Oh, what's G? Say again?
The sum end, is it f of s or f of r?
Yeah. Okay, I think we're basically out of time, but let me just say something. I'll finish up maybe I'll just put the proof of this in the notes. This follows, this is like almost immediate from inclusion exclusion. Okay. But the point is now you can compute all the f hat of s values in 3 to the n time and polynomial space. So basically the new problem is to compute f hat of s for all s. Okay, and I claim that you can do this. You can do this in the time and space that I said, and maybe I'll devote the beginning of Tuesday to explaining why, and then we'll do something else. Okay.